Okay, like in this case, right, as long as they are constant phase relationship, there's a constant phase relationship at any time, cross, and then at the zero there, the same thing. Anytime can look at that. Then we define reflective index, right? Speed of light over the speed of light in the medium. And reflective index in air is 1, in vacuum is also 1. Then we have light passing from air into another medium. Right? Frequency in vacuum and in the medium is the same. Frequency in this air and in the medium is the same. It doesn't change. Only the wavelength becomes shorter. Right? Shorter. So the reflective index we can show from here. Right? Using this formula, there's wavelength in air over wavelength in the medium. So that's worksheet number 5. Then we define our new term, optical path is the product of reflective index n and the length of the wave. Right? So n is the reflective index, L is the length of the wave. So same thing, if it's in air, right, n times L is the path length. Yeah. What's the problem? Yeah. Talk to me. Why is the problem? Okay, if no problem, let's carry on. So we want to find the path difference in the medium. Right? That's your L1. Right? It must be the same number of wavelength. Right? Same number of wavelength. So this becomes L1. So if time t taken for the light to travel the length, right? That time t to travel this length L, then time equals to L divided by C. Then we can replace the formula for reflective index into here. Replace C with NV. So in the medium, L1 is V times T. Right? Same time it travel this length. The same time it travel that length there, L1. So L1 is just your V times your T. Speed of light in the medium, V. Then we can, the time, right? We can replace this time with here. So V and V can cancel off. We got L over N. So this is the reflective index in the medium. So path length in the medium is shorter. Yeah, because this N is greater than 1. This is the original length of the wave. This is the new length in the medium. Okay. Path length becomes shorter in the medium. That's what this calculation wants to show you. Any comment? Okay, that's your worksheet number 6 answer. Okay, let's look at example 23.1. In air, the optical path length OA, right? That's your OA. So in air itself, without that medium, is D. So when that same light wave pass through a medium, the reflective index N and thickness T, right? Same length, whether it's in air or in the medium, right? Same length, D. So optical path difference. Hello? What happened? What happened? What? So are you in now or what's happening now? create new link. You cannot enter. Yeah, but you can rejoin. Okay. Are you in? Okay. Okay.
Hello?
Yeah. Okay.
Oh, just now suddenly disconnected, teacher. I don't know why.
I still saw you. I don't know why.
Oh, suddenly I got offline already.
Okay, we define
Okay, then can you go 2 slides before, Chair, please? Please, huh?
Yeah, we define the reflective index. And then there's the speed of light is frequency times wavelength, that's all. And then the same, right? That same length of wave now move into the medium, that's all. So the wavelength is lambda in air, in the medium is lambda m. And we can replace this one with that there. Right? If it's the medium, then we can replace that with lambda m. That can show that reflective index is lambda or lambda m, that's all. Right? That means it show you it becomes shorter, then we define a new term. Optical path is the product of the reflective index and the length of the wave. Right? That's the optical path. So now we have this wave of length L. Right? That L moved into a medium. So now the length becomes L1. Right? Same wavelength, except in the medium it becomes shorter, L1. So we are going to calculate the time T taken for the light to travel the length L, that one. Right? So it's light wave. So it's a distance divided by speed. So distance is the length of the wave. Speed is the speed of light. Then we can replace the C with NV. Right? And we have already defined from here. Take our V across that. Okay, so replacing that C with NV. So in the medium, right, L1. Okay, the time is the same. We are interested how is L1, how is the length change? The speed in the medium times the time, the same time as when this one travel in this air. The same time, how is the length in this air, in this medium? So that's your V, your T. I can replace with that. Previously is air, now this is in the medium. So it's L and V. V and V can cancel off, becomes Ln. So it tells you that, right? Remember your n is greater than 1. So it means that length there becomes shorter. Right? Shorter, as you can show in the picture roughly. Right? It becomes shorter. Right? So there's n is the reflective index of the medium. So the path length in the medium becomes shorter. That's all. Okay, so that is the answer to your worksheet number 6. Then I look
So
at
go
the
back again,
example.
Chair. Little bit more. Wait. Okay. Okay. Can go, Chair. Can go to the new one. Because I thought I missed some slides when I got disconnected, so that's why I asked.
No, we didn't go that fast. It's just that I saw
Okay.
you. Something wrong with your computer.
Okay. Yeah, I can go to the new slide ready, Chair.
Right? Example 23.1. Right? The optical path OA, where the light travel in air is OA, is D. Now that same length of light travel through a medium of refractive index n, thickness t. So the optical path, right? Optical path d minus t, that one is in air. So that is your d minus t, right? Minus that. And then t, it travel nt, right? Nt. Now, t is not time, t is just the thickness. That's how we define refractive index times the thickness. That's all. Add to this length and this length, that's all. So that's the optical path. So we can rewrite that, right? Take the t, factorize the t together. So this t and that t there. So we got n minus 1 here. So if we compare this same length, right? This length OA, this length also OA, this in air, same length D, but this one is passing through your medium or refractive index N and thickness T. Right? Because what's the difference in where they meet? What's the path difference? Right? Path difference is just D minus this one. So we get that's the answer. Okay. That means this one that's traveling through the medium has to travel this extra distance called the path difference. N minus 1t. Yep. I'm taking this one. D minus this length, that's all. This length is that one. So I call that the difference between the two lengths. I call it the path difference. Right? What is interference? When two or more waves meet at a point, there is a change in overall intensity or displacement. Right? So interference is what we see. There's a change in intensity or there's a change in displacement where the two waves meet at a point, they interfere. So we use the principle of superposition, and then what we see is called interference. Right? There's a change in intensity or the change in displacement. In standing wave, the two waves are traveling in opposite direction. But here we are looking at the wave can travel in different direction, but we are interested where they meet at a point. That is interference. You see a different, right? Same, we can still use the same principle. This is your displacement time graph. Right? So superposition tells us how the wave, we add the wave. Interference tells us what we see when the wave crosses. Are you with me?
Yeah. Oh, superposition tells how to add the wave. Interference tells us what we see when we. Oh, interference is more to observation. Superposition tell how to add it lah. Okay.
Superposition is telling us where the two waves, how do we add them up to get the resultant, that's all. Whereas interference tells us what we see as a result of this two wave meet.
The superposition.
We
The
see
result of the
now we use
superposition.
superposition to tell us there's a change in displacement or there's a change in intensity. That's all. Right? So there is interference at this point there. The two waves traveling from one traveling from slit 1, one traveling from slit 2, meet here. So at this point, it's called interference. Right? Page 156 in your book. Right? So conditions for wave to interfere, both waves must be of the same type. That means sound wave and sound wave, light wave, meet at a point. They must meet at a point before they can interfere. If they they don't meet at that point there, right? So we are interested where they meet at a particular point. That is where interference occurs. Same direction of polarization. Wave must be coherent. Right? Polarization we'll study later on. It just tells us that they are like this one. Vertically, this and this won't interfere. Right? You won't see any difference in them because they won't interfere. This is vertical polarization. This horizontal polarization. So they won't interfere. Right? That's what I mean by same direction of polarization. Okay. So we just review our constructive interference. Right? Cross and cross meet. Or the two-wave coincide, same frequency. Same frequency, they meet. The resultant, either they are cross and cross, or we say they are in phase. Or 2 pi m, m is 0, 1, 2, 3. Okay, phase different. They combine to create amplified wave, a wave that larger amplitude, known as constructive interference. So each amplitude is A, the resultant is 2A, intensity is 4I, right? Intensity is four times, not 2 times. Amplitude is 2 times only. So for light, what do we observe? Brighter light. Sound, we hear louder sound. That's all. So the amplitude is the one that changes. Frequency remains the same. Right? So that is just what we have studied before. I just review with you for standing wave. Right? That's the resultant wave. And then we have also do this one. Right? That's for each wave. Intensity related to the amplitude for one wave. The resultant, if the two waves add together, A plus A is the resultant amplitude is 2A. So resultant intensity, right? K, the amplitude we replace with this amplitude, 2A, so it's 4A squared. 4A squared, KA squared is this one, I, so it's come 4I, that's all, 4 times. Destructive, right? Or we call it cancellation, occurs when two sets of waves cross. Right? And we can see the cross of one meet the trough of one. Remember, they are on top of each other, not separate. And what we see is destructive interference, 0, or we call it right, phase difference of 180 degrees out of phase, or pi over m. Pi m, m is 135 odd. It can be 180. Then the next one can be 3 times that. Okay, so it's 540. For complete, if you want to see complete cancellation, that means 0 line, then the amplitude must be the same. Right? If it's light, you see dark band. If it's sound, you hear no sound. Okay, so this is the same thing. Let's just draw for you. That's the resultant, the two wave.
Teacher, can you give me 1 minute, please?
Okay.
Sorry.
Okay.
Hello? Yeah.
Yeah. Are you all right now?
Sorry, yeah, all right. Suddenly my mom called, I thought emergency, that's why I talked. Yeah. So you'll send the slide right today for this.
I always send you the slide after the lecture.
Okay. Sure.
Okay, so in interference, we are looking at where they coincide. The wave can travel from different direction. Right? So we are interested in a particular point where they coincide here or here. Right? So there will be destructive interference. So in this part, remember the wave is traveling, is moving. Right? This is displacement distance graph, where we see the interference occur. We see displacement time graph. Cancellation occurs where the two sets of wave cross, where the crust meet a wave trough. Phase difference between the wave is 180 degrees out of phase, right? Crust and trough. Okay, as before, if we want complete cancellation, 0, then it must have the same, right? Same amplitude. That's important. Then we hear no sound, we see no light. Okay, so we will see that in Young's modulus, right? Dark band and bright band. And in your SPM, you have a deeper single point source, a deeper, produce your spherical wave. 2-point source, right? To produce your Young double slit experiment. Okay, so that's your point source S1, S2. Right? We can look at them separately. S1, S2, and then B is here. Right? B is the perpendicular bisector. BA is a perpendicular bisector. So any point along here is equal distance from S1 and S2. Okay, so AB is a perpendicular bisector. That one, AB, perpendicular bisector of the S1 and S2. S1 is the source 1, source 2. All points from AB are equal distance from S1 and S2. That's what we have said. Right? S1, S1A to S2A is the same. A can be any point along here. So there's no difference in length between the two of them. So there is your crust. The trough is lighter in color. Right? There's your trough. In between the crust. Then we have the nodal line. Right? There's a nodal line where the crust meet the trough. The crust meet the trough. Okay. Example will be CD, this one, the blue one, CD, or it can be your GH, this one. Okay, this one you have to refer to your SPM book lah. We are just using Huygens principle to produce each of the new wavefront as well. Right? This is your point source. Give out spherical wave. Then we have antinodal line, right, where they have constructive interference. The example will be AB, the red one. Right? Or it can be this one, or that one there, or the blue one, or it can be that one there. Okay, or it can be this one. Right? EF, the same thing. Right? EF, constructive interference. Okay, so usually if we count in exam, they won't draw for you they just draw for you the crust only. The trough, you are supposed to imagine yourself in the middle there, between the two crusts. Okay, let's look at example 23.2. S1 and S2 are vibrating in phase. That's your S1. That's your S2. Right? So they are point source. They produce spherical wave. So we are interested in the path difference between S1T and S2T. Right? Usually we won't draw all this circle. This is just to elementary because it's very troublesome to draw that. Right? We are interested in path difference between S1T and S2T. That's your T. So that's your S1T. That's your S2T. So path difference, right? S2T is longer.
So what was that, teacher? I heard a sound.
It's okay. Don't need to worry about the sound. Why are you distracted with the sound for what? It's just from the
No,
computer.
suddenly I heard some sound.
Yeah, it's a breaking sound. Just to wake you up a bit. Right? So this is 0, 1, 2, 3, 4. That's why we got a 4 wavelength. And then this one, 0, 1, 2, 2 wavelength. So 4 minus 2 is 2 wavelength. So this is constructive interference. Right? We can see from here, crust, mid crust, constructive interference. Okay with that? Anything not clear? Right? So usually if it's light, if the S1 and S2 are like point light source, then we put a screen there to see the light band and dark band. Okay, same thing. Now we look at point Q. Right? What's the path difference between S2Q and S1Q? Okay, now you can read yourself. S2Q minus S1Q. How many wavelength is this one? Yeah. Yeah, that's your S2Q. That's your what? S1Q. How many wave? What's the answer? Yeah. S2Q, you can count. Huh? What? That's
No,
one wavelength,
nothing, sir.
2 wavelength, 3 wavelength, 4 wavelength, 5 wavelength. Right? This one, you look at this source there. 1, 2, 3, 3.5. So 5 minus 3.5 wavelength. That's 1.5. So as long as you get half, it's refractive interference. Okay. Okay, how about the path difference between S2P minus S1P? Your P is this one here. Yep. Should be able to count for me.
S2P. 1, 2, 3, 4, 5, 6, 7, 8.
S2P is what? Count the dark circle. Don't count
S2P.
don't count the in between. This is your crust. The dark one is the crust. The trough is in between. Don't count the crust. Don't count the trough. Count the crust. Yeah. S2P is what?
Oh.
How many wavelength?
And how do you calculate each? I'm a bit confused.
I already showed you how to do that already. Means you are not paying attention in class. Previous one, you just count. The dark one is 1, 2, 3, 4, 5. That's why we forget a 5 wavelength. Then S1, you count from the sphere, 1, 2, 3, and then this is half. So 3.5. So you should be able to do now. S2P minus S1P.
Oh, S1P is 2. SP S1P is 1.5.
S1P is 1.5. How do you count? There's your P here. These are all the way from S1. These are all the way from S1. S2 is this side. S2 is this is away from S2. That's away from S2.
Okay. Che, don't give me the answer yet. Wait, 1, 2. 5.
S2P is what?
5.
S2P is this one. This is 1, 2, 3, 4,
4.
5. There's another one here.
5.5.
What 5.5? This is a complete one. It's just thin draw for you, that's all. There's a dark one there.
Oh.
So it should be 6 wavelength. S1P.
S1P. Okay, wait, S1P. 1, 2, 3, 4.
Ah,
Got
correct.
4.
Good. That's all.
Yeah.
6 minus 4.
Ow.
So is it constructive or destructive?
Constructive or destructive? Is to be destructive.
No. Wherever you got a full wavelength, it's constructive. The crust, mid-crust is already see for you. Can't you see properly? Crust, mid-crust means constructive.
Constructive.
If destructive, you can see from here. Crust, the crust meet the trough there. Then there's destructive. Here, right? Here, the red one is always constructive. Where there is trough and trough, also constructive. So this is constructive. 2 lambda.
Ow.
So lower form SPM, we will do it this way. But higher form, we will introduce a phase difference. So for m equals to 1, we can either look at the path difference, or like Huygens principle, we look at the wavefront. M equals to 0 are all the parallel line there. This parallel line, all moving in the same direction. So that's why we say the constructive interference there, right? This plane wave there, joining the crust there, all moving in this direction. M equals to 0. Right? M equals to 1. Right? Where the second one meet the third one. Right? The tangent, there's your wavefront. Right? There's your wavefront. Right? There are others. So it will move in this direction. That's why we get M equals to 1. Constructive interference. Right? So throughout, we will either use path difference or use Huygens principle. This you are using wavefront, Huygens principle. Okay, so that's your M equals to 1. So in general, right, path difference. What is path difference? Is the extra distance which a wave travel compared to the other. So if there's whole number, m lambda, right? M equals 0, 1, 2, 3, or it can be 0. Right? 0 is the center here, the blue one, 0, 1, 2, 3, right? Or we can summarize as m lambda. As long as it got half lambda, like this one, the red one, half lambda, sorry. This one, this is half lambda, this is 0, right? Cross and cross, this is cross and trough, half lambda, right? This lambda, this 1.5, all this will be 1.5, this will be 2 lambda. Okay, it is half, where we see 1.5 or 1.5 or 2.5 is destructive. Okay, or we can summarize as 2m minus 1, half lambda. Right here, I'm factorizing half m out, half lambda out. Right, your book give this one, which I don't agree lah, because you can see from here, no m equals to 0 for destructive. It's just half here, that's all. Half here and half here, that's all. Right? On either side, so this is the first one, no 0 for destructive. Right? No 0, no m equals 0 for this one, got m equals 0. M equals 0 is this one for constructive. Okay, so you can either write or minus. You don't want to write what I did, I write this one. I take the half out. If not, you can write it as this form, minus half, where m start from 1, 2, and so on. Okay. Right. So that is your constructive. M equals to 0. Right. You see the center one. And then if this path different is 2 lambda, then this one will be 2. Right? This is 0, I'm sorry, this is 0, 1, m equals 0, this m equals to 1, this m equals to 2. Right? Where the path difference is 2 lambda. You see that we give it different name lah, different order lah, to differentiate this 0 order, this is the first order, this is the second order. We should study Young's double slit. Right? Some book will use n, this doesn't matter. M or n is the same. Right? M 0 order maximum. Right? This one sometimes we call it central bright fringe or band. First order maximum, first bright fringe. Right? Half difference of half lambda equals to phase difference of pi radian. This one you must remember. Okay. Right? So this one is just to show you. Right? S1 will give out its own wave. S2 will give out its own wave. Right? That's Huygens principle. So we can draw your nodal line or antinodal line. And then the trough is usually between the two crusts. Usually they don't draw for you. Okay. So we have completed. Anything you want to ask? Yeah.
No.
So it means that you have to go to do your homework. No shortcut, as I say. You want to learn, to remember, you have to do your homework. You don't do your homework, you forget everything. And you are at the moment hit or miss. Hit means if it come out the thing you study, you pass. If it doesn't come out the thing that you study, you fail, which is not the right way to study. Right? Put an effort. Cut down your other activities. Concentrate on your study. More is important. You want to get a pass. Okay. If no question to ask, I will stop here.
Yeah. Okay. Thank you, sir.
Okay.